Hello there, friend. Welcome back to the Sleepy Professor. It really means a lot that you've chosen to spend this quiet part of your day right here with me. Maybe today was one of those days that just felt a bit heavier than usual, where every little thing seemed to demand something from you. Or perhaps you're the kind of person who finds true peace not in counting imaginary sheep jumping over fences, but in letting your mind wander to faraway places. Places where planets spin silently in the darkness, where moons drift through the endless void, where everything moves in slow, graceful orbits that have continued uninterrupted for billions of years. Whatever it was that guided you here tonight, whatever thoughts or feelings are swirling around in your mind right now, this moment belongs entirely to you. You've arrived at a safe harbor, a gentle place where you can finally let go. You don't have to do anything at all right now, not a single thing. Just rest your body wherever you are. Let your breathing slow down naturally, nice and easy, like waves rolling gently onto a shore. Let those racing thoughts that have been spinning around all day start to soften at the edges, becoming less sharp, less urgent. And let your body grow wonderfully light, almost as if gravity itself has decided to loosen its grip on you just a little bit, allowing you to begin floating quietly, peacefully, through the vastness of space. Because tonight we're embarking on a gentle journey through our solar system. We won't be rushing anywhere. We won't be taking the fastest route or checking things off a list. Instead, we're going to move in soft, lazy spirals, wandering without hurry from sun-scorched planets baking under relentless heat to dusty rings made of ice and rock that catch faint sunlight, from shadowed craters that have remained untouched for eons to frozen oceans hidden deep beneath ancient layers of ice that may never see sunlight. This is a story told not in complicated numbers and mathematical equations, not in formulas that need solving, but in magnetic storms that rage across entire planets, in tilted axes that create seasons lasting decades, in moons that glow softly like nightlights in the cosmic darkness, and in distant worlds where it might actually rain diamonds from the sky. From planets that spin sideways like cosmic tumbling toys to ancient sunlight that left the surface of our sun millions of years ago and is still crossing the void of space right now. Every single orbit, every rotation, every silent movement holds something strange and beautiful and quietly magnificent. We'll take our time, moving gently, slowly, deliberately, just one sleepy fact at a time. Let each one wash over you like a wave rolling onto a quiet beach at night, carrying with it something peaceful and wonderful. And just before we begin our drift into the cosmos, if these quiet nighttime explorations help you unwind and relax, if they give you a peaceful, gentle way to end your day and calm your racing mind, consider softly tapping that like button and subscribing to the channel. It helps other people who need this find their way here too, one sleepy soul at a time, all of us drifting together peacefully under the same infinite blanket of stars. Now then, my friend, let's begin our journey. Neptune's winds break the speed of sound. Way out there at the very far edge of our solar system, farther than most people can truly comprehend, Neptune spins quietly in near total darkness. Despite being the farthest known planet from the Sun, so incredibly distant that sunlight arrives as barely more than a whisper, as nothing more than a faint suggestion of warmth, Neptune hosts the fastest, most violent winds in the entire solar system. These winds whip and tear through its upper atmosphere at absolutely staggering speeds exceeding 2,000 kilometers per hour, which is faster than the speed of sound here on Earth. Just imagine that for a moment, if you can. Winds moving at roughly 5 times the speed of a commercial jet airplane, howling and screaming through thick clouds made of methane and hydrogen gas. Scientists believe these relentless winds likely draw their immense energy from deep within the planet itself, from heat that continues to radiate slowly outward despite the absolutely freezing conditions at its cloud-covered surface. Neptune's atmosphere is composed mostly of hydrogen, helium, and methane, and those supersonic winds carve massive, swirling storm systems into the planet's pale, ghostly blue clouds. It's a frozen world, yes, but one in constant, restless, supersonic motion. A planet that never rests, never sleeps, never stops moving. Mars holds a canyon the size of a continent. Now let's drift a little closer to home. back toward the inner solar system, to Mars, that rusty orange neighbor of ours that hangs in the sky like an ancient ember. Stretching more than 4,000 kilometers across the Martian equator, carved deep into the planet's surface, there's a canyon system called Valles Marineris. It's the largest canyon system in the entire solar system, dwarfing anything we have here on Earth. If you could somehow lift it up and place it on our planet, it would span the entire width of the continental United States, stretching from the Atlantic Ocean all the way to the Pacific coast. In certain places, this immense canyon plunges over 7 kilometers deep into the Martian crust. That's more than 5 times deeper than the Grand Canyon in Arizona. Just think about standing at the edge of something like that, peering down into depths so vast they seem to swallow the entire horizon, the walls dropping away beneath you into shadows that never fully lift. Scientists believe Valles Marineris formed through a violent combination of tectonic stretching, powerful volcanic activity, and erosion that happened over billions and billions of years. Unlike Earth's canyons, which are typically carved slowly and patiently by rivers flowing over countless millennia, Valles Marineris may have opened catastrophically as the planet's crust cracked and pulled apart in some ancient, violent event we can only imagine. It is a permanent scar on Mars' dusty surface, a haunting reminder of a violent geological past now frozen in time, completely silent and utterly still. Venus has no magnetic field. Venus is so often called Earth's twin because the two planets are remarkably similar in size, mass, and basic composition. But Venus is missing something absolutely crucial, something that makes all the difference between a living world and a hellish furnace. It has no global magnetic field protecting it. Here on Earth, our invisible magnetic shield is generated deep underground by the constant motion of molten iron swirling and churning in our outer core, constantly moving in vast currents, constantly protecting the surface from harmful solar radiation. Venus, however, seems to have either a sluggish or possibly completely solid core, which prevents the kind of dynamo effect needed to create that life-saving protective field. Without this invisible magnetic shield surrounding it, Venus's thick atmosphere is constantly bombarded and stripped away bit by the relentless solar wind streaming from the sun. The absence of a magnetic field helps explain why Venus, which scientists believe may have once been much more Earth-like billions of years ago, perhaps even with liquid water oceans covering its surface, eventually became the scorching furnace world it is today. A cautionary tale written in atmospheric chemistry and extreme temperatures. Diamonds may rain on Uranus and Neptune. Here's something that sounds like it came straight from pure fantasy, from a science fiction story, but might actually be completely real. Deep within the thick, crushing atmospheres of Uranus and Neptune, thousands upon thousands of kilometers below the visible cloud tops, conditions may be extreme enough to create something truly extraordinary. Falling diamonds drifting slowly downward through layers of liquid and gas. These icy giant planets have enormously thick layers of methane gas in their atmospheres, and under the immense pressure and scorching heat found deep below the surface, scientists believe the methane molecules can break apart, releasing individual carbon atoms. These freed carbon atoms then compress under the crushing pressure into perfect crystalline structures, forming tiny diamonds that rain slowly down toward the planetary core, drifting and tumbling through layers of liquid and gas. Laboratory experiments here on Earth have actually simulated this bizarre process, showing how hydrocarbon compounds can condense and transform into actual diamond crystals under the right extreme conditions. If this theory is correct, if the math and physics work out the way scientists think, then storms of glittering crystals might be drifting right now, at this very moment, through the deep blue darkness of those distant gas giants. Just imagine that, diamond rain, falling forever through an alien sky we'll never see with our own eyes. Earth is the only planet with plate tectonics. One of Earth's most distinctive and absolutely life-enabling features is something we almost never think about as we go about our daily lives. It's the intricate system of plate tectonics, a dynamic, constantly shifting network of massive crustal plates that float atop the semi-liquid mantle beneath. These gigantic moving plates create earthquakes that shake the ground, yes, but they also gradually build towering mountain ranges and recycle carbon dioxide through volcanic activity, regulating our planet's climate carefully over vast geologic timescales. So far, despite decades of exploration, no other planet in our solar system shows clear evidence of this ongoing process. Mars and Venus both have surface fractures and impressive volcanic features dotting their landscapes, but they appear geologically stagnant by comparison, frozen in time. Their crusts don't move and shift and recycle the way ours does constantly. Earth's active plate tectonics may be a fundamental part of what makes our world habitable, driving the long-term cycles that stabilize surface temperature, support vast liquid water oceans, and enable the slow, majestic dance of continents drifting across the globe over hundreds of millions of years. It's one of those quiet background processes that makes absolutely everything else possible. Some asteroids have their own moons. While we typically picture asteroids as solitary wanderers, lone chunks of rock tumbling alone through the emptiness of space, some of them actually have their own moons. Small companion bodies orbiting faithfully around them, held close by gravity despite their tiny combined size. These miniature satellites are usually either captured fragments from ancient collisions or companions that formed together from the same cloud of debris billions of years ago. The very first discovered asteroid moon was named Dactyl, which orbits dutifully around the larger asteroid Ida. It was revealed to the world by NASA's Galileo spacecraft way back in 1993, a tiny world just 1.5 kilometers across, circling its parent faithfully. Since that groundbreaking discovery, dozens more asteroid moon systems have been found drifting through space, including some with multiple moons orbiting a single asteroid, and strange binary arrangements where two asteroids of similar size orbit each other as equals, locked in an eternal gravitational dance. These miniature systems show us that even in the incomprehensible vastness of space, gravity can link even the smallest of objects into quiet, enduring partnerships. Nothing is ever truly alone out there. Mercury has a ghostly exosphere instead of a true atmosphere. Unlike Earth with its thick, protective blanket of air, Mercury doesn't have a substantial atmosphere to retain heat overnight or scatter sunlight into colorful sunsets and sunrises. Instead, it has something far more tenuous and delicate, a thin, barely there shell of scattered particles known as an exosphere. It's essentially a near-perfect vacuum where individual atoms bounce around freely without ever really colliding with each other. This ghostly exosphere is made up of atoms that have been blasted violently from Mercury's sun-baked surface by the relentless solar wind and countless micrometeoroid impacts over billions of years. It includes sodium, potassium, and oxygen atoms, all dancing invisibly in an ultra-thin cloud surrounding the planet. Because Mercury completely lacks the gravitational strength to hold onto a real, substantial atmosphere, these scattered particles constantly escape into space and must be continually replenished from below. The result is a ghostly, shimmering envelope of scattered atoms, completely invisible to the human eye, but detectable with the right scientific instruments. A whisper of an atmosphere on a world relentlessly baked by the nearby sun. The sun loses millions of tons of mass every second. Every single second of every single day, right now as you're listening to these words, the sun converts over 4 million tons of its own mass into pure energy through the process of nuclear fusion happening deep in its core. In the sun's unimaginably hot center, hydrogen atoms are forced together under crushing pressure and fused into helium, releasing tremendous amounts of light and heat that power our entire solar system. This energy radiates outward in absolutely all directions, warming distant planets, driving winds and weather patterns, fueling every single blade of grass and every living thing here on Earth. Though this constant loss is absolutely minuscule compared to the sun's total mass, which is almost incomprehensibly large, over billions and billions of years it does add up. eventually billions of years from now. Long after we're gone, the sun will exhaust its hydrogen fuel completely and begin to change dramatically, to swell and cool, transforming into something called a red giant. But for now, for the next several billion years at least, it continues to burn steadily and reliably, sacrificing a tiny part of itself with every passing second. A constant gift of light and warmth to all the worlds that circle it. Saturn's rings are slowly disappearing. The beautiful, iconic rings that encircle Saturn, those spectacular bands of ice and rock that make it the jewel of the solar system, the planet everyone recognizes instantly, are not permanent features. They are gradually, inevitably falling into the planet, drawn slowly inward by gravity and pulled down by Saturn's powerful magnetic field. This ongoing process, which scientists call ring rain, involves continuous streams of ice particles and electrically charged material drifting inward over time, spiraling down toward the planet. Detailed observations from NASA's Cassini spacecraft, which spent over a decade studying Saturn up close, suggest that the rings may actually be less than 100 million years old, surprisingly young by planetary standards, and could vanish entirely in another few hundred million years. Though they seem timeless and eternal when we gaze at them through telescopes, when we see those stunning images sent back from space, Saturn's rings are actually a temporary feature in cosmic terms, a shimmering spectacle that will one day fade completely into memory. We are extraordinarily lucky to be living in an era when they still exist for us to admire. Mars experiences planet-wide dust storms. Mars is well known for its rusty, desert-like landscape, its endless plains of red dust stretching to the horizon, but also for something far more dramatic and powerful: the absolutely colossal dust storms that sometimes engulf the entire planet in a choking, swirling cloud. These massive storms can last for many weeks or even several months at a time, completely blocking out sunlight and reshaping the surface with their relentless winds. The dust itself is incredibly fine, almost like talcum powder, and can stay suspended in the thin Martian atmosphere for extended periods, creating a thick, hazy, reddish glow that turns the whole planet into an orange fog of rust-colored particles. Some storms begin modestly as small gusts in a crater or valley somewhere, but can grow rapidly and exponentially due to feedback loops between heat absorption, wind patterns, and the unique topography of the Martian surface. In 2018, one particularly severe global dust storm led directly to the end of NASA's Opportunity rover's mission, as its solar panels were slowly but surely choked with thick dust, starving the little robot of the power it desperately needed to survive. Even without rain or flowing oceans, Mars remains an active, dynamic, and restless world. Europa may have a salty ocean beneath its ice. Beneath the cracked, frozen shell of Jupiter's intriguing moon Europa, there is strong and growing evidence for something absolutely extraordinary: a vast subsurface ocean of liquid water, possibly containing more water than all of Earth's oceans combined. Tidal forces from Jupiter's immense gravitational pull flex Europa's interior constantly, like squeezing a rubber stress ball over and over again, generating tremendous friction and heat that may keep this hidden ocean from freezing completely solid, despite the moon's frigid surface temperature. The icy surface is streaked with dark lines, ridges, and cracks, clear signs of shifting ice plates moving above, and various spacecraft have detected intriguing magnetic signatures and chemical traces that strongly support the subsurface ocean hypothesis. What makes Europa especially fascinating to astrobiologists is the tantalizing possibility that this hidden sea could actually harbor some form of life. It's a dark, utterly alien ocean, never once touched by direct sunlight, warmed from below by tidal friction, sealed beneath many kilometers of solid ice. Yet it could potentially be rich with all the chemical ingredients necessary for biology to emerge. A secret sea on a distant moon, waiting to reveal its mysteries. Mars has a volcano taller than Everest. On Mars, rising dramatically from the rust-colored plains, there stands a mountain that would completely dwarf anything we have here on Earth. Olympus Mons, the tallest volcano in the entire solar system, towers nearly 22 kilometers above the surrounding Martian surface. That's almost 3 times the height of Mount Everest, Earth's tallest peak. It's so incredibly wide at its base that it would easily cover the entire state of New Mexico if you placed it on a map. The volcano's enormous size is possible because Mars lacks plate tectonics, allowing lava to pile up in one spot for billions of years without the ground shifting beneath it. This ancient shield volcano hasn't erupted in millions of years and likely never will again. It stands as a silent monument to Mars' violent volcanic past, a frozen giant on a dying world. Neptune and Pluto are locked in orbital resonance. For every 3 complete orbits Neptune makes around the Sun, Pluto completes exactly 2. This gravitational choreography, called orbital resonance, keeps them in a stable, predictable dance despite their paths appearing to cross on paper. It's a delicate cosmic balance, governed by invisible gravitational forces and the patient mathematics of celestial mechanics that have kept this rhythm going for billions of years. The 2 worlds never actually come close to colliding, held apart by this elegant mathematical relationship. A silent partnership written in gravity and time. The Sun reverses its magnetic field every 11 years. Roughly every 11 Earth years, something truly remarkable happens at the heart of our solar system. The Sun's entire magnetic field flips completely. The north and south magnetic poles switch places, totally reversing. This cyclical process, known as the solar magnetic cycle, is tied directly to the Sun's complex internal dynamics and affects solar activity in dramatic, observable ways, including the number of sunspots visible on its surface, the frequency of solar flares, and powerful coronal mass ejections that get hurled into space. At the peak of each cycle, called solar maximum, the Sun becomes far more active, with more intense radiation bursts and magnetic storms. As the cycle gradually wanes, activity decreases steadily, eventually reaching what's called solar minimum. These regular cycles influence Earth's upper atmosphere significantly, can affect satellites orbiting our planet and power grids on the surface, and even create more spectacular, vibrant auroras dancing in polar skis. The Sun's magnetism is not fixed or permanent at all. It pulses and flows rhythmically like a breathing, magnetic heartbeat. Planetary alignments don't cause natural disasters. It's a persistent myth, one you might have heard repeated many times, that planetary alignments can somehow trigger earthquakes, floods, tsunamis, or other major disasters here on Earth. But there's absolutely no scientific evidence whatsoever for such effects. The gravitational pull of other planets on Earth is absolutely minuscule, barely measurable, compared to the enormous influence of our Moon or the Sun. Even during rare alignments when several planets line up perfectly in the sky, their combined gravitational influence is negligible, essentially unmeasurable in any practical sense. Our Moon, being so incredibly close to us, has far more impact on ocean tides and even on seismic stress patterns than massive but distant planets like Jupiter or Saturn ever could. Planetary alignments are beautiful and mathematically interesting celestial events, yes, worth watching and appreciating. But they're gravitationally harmless, a silent dance of distant worlds, not a celestial omen of doom or disaster. Leaving the solar system takes decades. Escaping the Sun's gravitational pull is no small task at all. It requires enormous speed and many decades of continuous travel through the void. Spacecraft like Voyager 1 and Voyager 2, launched way back in 1977 during a rare planetary alignment, have only recently entered what we call interstellar space, the region far beyond where the Sun's influence finally gives way to the interstellar medium. These remarkable missions took more than 40 years to reach that distant boundary, traveling outward at speeds exceeding 60,000 kilometers per hour, never slowing down. The Voyager probes have crossed the orbits of all the major planets, passed through the distant Kuiper belt, and continued boldly into the dark, unknown beyond. They carry instruments that still function remarkably well after all these years, as well as a golden record filled with carefully chosen sounds and images of Earth. Music, greetings spoken in many languages, the sound of ocean waves and human laughter. They are our quiet ambassadors to the galaxy, carrying messages we may never know if anyone ever receives. Earth's magnetic field shields us from space radiation. Surrounding our entire planet is an invisible but absolutely crucial magnetic field, generated deep underground by the constant movement of molten iron churning in Earth's outer core. This protective magnetic field, called the magnetosphere, deflects dangerous charged particles constantly streaming from the sun. It protects our atmosphere and everything on the surface from harmful solar and cosmic radiation that would otherwise sterilize the planet. Without this invisible shield, the relentless solar wind would gradually erode and strip away our atmosphere, just as it likely did on Mars billions of years ago when that planet's magnetic field failed. The magnetosphere also funnels some energetic particles toward the magnetic poles, where they interact with atmospheric gases and produce auroras, those shimmering, dancing curtains of green, red, and violet light in polar skis. Earth's magnetosphere is a dynamic, invisible shield, absolutely essential for preserving both complex life and stable climate over geological timescales. The Moon is slowly moving away from Earth. Each year, our faithful Moon drifts approximately 3.8 centimeters farther from Earth. It's an incredibly slow retreat, barely noticeable in a human lifetime, completely invisible to our eyes, but over millions and millions of years, it adds up significantly. This gradual separation is caused by complex tidal interactions between the two bodies. The gravitational pull between Earth and the Moon creates bulges in our planet's oceans, those familiar tides rising and falling, and those bulges, in turn, push the Moon very slightly outward over time through conservation of angular momentum. In the distant past, billions of years ago, the Moon was much, much closer to Earth and appeared significantly larger and more dramatic in the sky. Ancient tides would have been absolutely enormous, reshaping coastlines constantly. As the Moon continues its slow retreat, our days gradually lengthen, very slowly, and total solar eclipses become less frequent and less perfect. Billions of years from now, the Moon's orbit will be so wide that total solar eclipses will no longer be possible at all. The sky is changing, even if we don't yet feel it in our brief lifetimes. The Kuiper belt holds icy worlds with mirror-like surfaces. Far beyond Neptune's orbit, in the cold outer reaches of our solar system, the Kuiper belt contains not only dwarf planets, but also countless smaller icy bodies with startlingly bright reflective surfaces. Some of them shine like polished mirrors floating in the darkness. One fascinating example is Haumea, a rapidly spinning, oddly football-shaped object coated in crystalline water ice that catches sunlight brilliantly. Another is Eris, which reflects nearly all the sunlight that touches it, making it one of the most reflective bodies in the entire known solar system, brighter than freshly fallen snow on Earth. These distant objects may have been resurfaced by cryovolcanism, by impacts that exposed fresh layers of pristine ice, or by chemical interactions scientists don't yet fully understand. In the darkness at the very edge of the sun's reach, some of these distant worlds gleam like cold mirrors, catching faint, ancient sunlight in their frozen silence. Enceladus sprays water into space. Saturn's tiny moon Enceladus may be small, barely 500 kilometers across, hardly bigger than some asteroids, but it hides a spectacular secret beneath its icy surface. From its south pole, towering geysers of water vapor and ice crystals erupt violently into space through long cracks known as tiger stripes. These dramatic plumes are powered by tidal heating deep beneath the surface, where friction caused by Saturn's immense gravitational pull keeps a subsurface ocean in a liquid state despite the freezing temperatures. The material in these erupting plumes contains organic compounds, dissolved salts, and even tantalizing signs of hydrothermal activity, similar to what we see at the bottom of Earth's oceans. This raises the absolutely tantalizing possibility of microbial life existing, hidden in a dark ocean sealed beneath the ice, warmed from below. Some of the erupted water escapes into space and helps replenish Saturn's gossamer E-ring, creating a living, dynamic connection between moon and planet. Enceladus is small and easily overlooked, but it may actually be one of the very best places to look for life beyond Earth. Some asteroids are just piles of rubble. Not all asteroids are solid, dense chunks of rock forged in the early solar system. Many are actually loose collections of stones, gravel, dust, and debris, held together only by their own extremely weak gravity. These are called rubble pile asteroids. These fragile, porous bodies can form after violent collisions shatter larger asteroids into countless pieces, with the debris slowly drifting back together over vast periods of time, like cosmic beanbags tumbling through space. Rubble pile asteroids can have large internal voids and empty spaces, spin in strange and unpredictable ways, and change shape noticeably under pressure or impact. Space missions like Japan's Hayabusa 2 and NASA's OSIRIS-RX have visited such bodies up close and confirmed their delicate, porous nature firsthand. These asteroids are not monolithic ancient relics at all. They're chaotic assemblages, ancient drifting ruins of early planetary construction that barely hold themselves together as they quietly orbit the Sun. Mercury's core is disproportionately large. Mercury is the smallest of the rocky planets, a tiny world closest to the Sun, but it has an unusually massive iron core hidden beneath its surface. This dense metallic center makes up about 80% of the planet's entire radius, a far larger proportion than we see in Earth, Venus, or Mars. The reason for this oversized core remains uncertain and continues to puzzle planetary scientists. Some researchers think Mercury once had a much thicker rocky mantle surrounding it that was violently stripped away by a giant impact early in the solar system's chaotic history. Others believe it formed extremely close to the Sun, where intense solar heat favored the accumulation of heavier metallic elements over lighter rocky ones. The result is a planet with a relatively thin crust, a huge, dense core, and a surprisingly weak magnetic field for its size. A metal-heavy survivor from the solar system's violent, chaotic youth. Venus has no moons at all. Among all the rocky planets orbiting our Sun, only Mercury and Venus orbit completely alone without any natural satellites keeping them company. While Mercury's extreme proximity to the Sun may explain its lack of moons, making stable orbits nearly impossible, Venus's situation is far more puzzling to astronomers. It's roughly the same size and mass as Earth, which has a large, prominent moon, yet Venus has absolutely none. Some theories suggest it may have once possessed a moon that eventually fell back into the planet, or was lost in some ancient, violent collision we'll never witness. Others argue that Venus's extremely slow, retrograde rotation, spinning backward compared to most planets, might somehow prevent stable lunar orbits from forming or persisting. Whatever the true cause, Venus orbits alone through space, a bright, cloud-wrapped world with no lunar companion hanging in its sulfuric twilight sky. Solitary and silent. Most of the solar system's moons orbit gas giants. While Earth has just one moon, and Mars has two tiny, potato-shaped ones barely worth mentioning, the giant planets of the outer solar system are surrounded by sprawling, complex systems of satellites. It's almost like they each have their own miniature solar systems orbiting around them. Jupiter and Saturn each have dozens upon dozens of confirmed moons catalogued by astronomers, ranging from tiny captured asteroids just a few kilometers across to massive worlds like Ganymede and Titan that are larger than the planet Mercury. Uranus and Neptune also host many icy moons with exotic compositions, some with complex, tilted orbits, some potentially hiding oceans beneath their frozen surfaces. These gas giants act like powerful gravitational vacuum cleaners, their immense mass drawing in passing debris and gradually assembling satellite systems over billions of years. The farther from the Sun you travel, the more moons you'll find orbiting each planet. A gentle reminder that gravity naturally gathers companions, even in the cold, dark depths of space. Hubble has photographed planets from Earth orbit. Though it orbits just a few hundred kilometers above Earth's surface, the Hubble Space Telescope has captured detailed, breathtaking images of the outer planets. Cloud bands swirling on Jupiter, storms raging on Neptune, seasonal changes on Mars. These images provide long-term observations that complement the flybys of spacecraft, offering views of evolving weather patterns, ring systems shifting over time, and planetary auroras dancing at the poles. Hubble's clarity above the distorting effects of Earth's atmosphere allows scientists to track storm development, monitor impact events, and study atmospheres in ultraviolet and visible light. From its quiet perch in low Earth orbit, Hubble watches not only the most distant galaxies billions of light years away, but also the shifting faces of our neighboring worlds. Jupiter's Great Red Spot is centuries old. The Great Red Spot is a massive storm swirling in Jupiter's southern hemisphere, wide enough to swallow 2 or even 3 Earths side by side, and it has been raging for at least 350 years, possibly much longer. First observed in the 1600s through early telescopes, the storm has changed over time, gradually shrinking in size, but still remaining powerful and persistent. Its reddish hue may be caused by complex chemical reactions in Jupiter's atmosphere, triggered by sunlight interacting with high-altitude compounds. Wind speeds exceed 400 kilometers per hour along its outer edges. While Earth's most powerful hurricanes last days or maybe weeks, this Jovian tempest spans centuries, trapped in the planet's turbulent cloud belts, a storm older than nations. Neptune radiates more heat than it receives from the Sun. Although Neptune lies incredibly far from the Sun, nearly 30 times Earth's distance, it is not a frozen, inert world. In fact, Neptune radiates about 2.6 times more energy than it receives from the distant Sun. This internal heat drives strong winds and storm systems, including the fastest recorded winds in the solar system, which we talked about earlier. The exact source of Neptune's heat remains somewhat uncertain, but possibilities include residual energy from its formation, slow gravitational contraction happening even now, or radioactive decay within its core. Despite its extreme distance from the Sun, Neptune is a world of surprising energy. A planet with a cold exterior, but a warm, restless interior, constantly reshaping its windswept atmosphere. Earth is the only planet with water in all 3 states. Our planet is unique in so many ways, but here's one you might not have thought about. Water exists naturally on Earth's surface as a solid, liquid, and gas, all at the same time. Ice caps and glaciers, oceans and lakes, clouds and water vapor, all coexist and cycle continuously through the atmosphere, land, and sea. This balance is crucial for life and is carefully regulated by Earth's distance from the Sun, its atmospheric pressure, and its relatively stable climate. Other worlds may have water in isolated forms, icy crusts on distant moons, vapor in thin atmospheres, or hidden subsurface oceans, but none show the same dynamic planet-wide presence we see here. On Earth, water flows, freezes, evaporates, and rains in a never-ending, life-sustaining dance. The heliopause marks the edge of the Sun's influence. As the solar wind flows outward from the Sun in all directions, it eventually collides with something. The interstellar medium, that thin gas and dust that fills the space between stars. This boundary is called the heliopause, and it defines the outer edge of the Sun's protective bubble, known as the heliosphere. Beyond this point, the pressure from other stars and galactic particles becomes stronger than the solar wind's push. Voyager 1 crossed the heliopause in 2012, followed by Voyager 2 in 2018, becoming the first human-made objects to enter true interstellar space. Though the Sun's gravity still extends much farther, potentially all the way to the Oort cloud, the heliopause marks the end of its energetic reach, the final breath of solar influence before deep space truly begins. The solar system is drifting through a local cloud. Our entire solar system is not sitting still in some fixed location in space. We're actually moving through a region called the local interstellar cloud, a thin concentration of gas and dust about 30 light-years across. It's part of a larger structure known as the local bubble, formed by ancient supernova explosions millions of years ago. As the Sun travels through this cloud at about 70,000 kilometers per hour, its heliosphere acts like a shield, deflecting interstellar material. Scientists study this cloud to understand how interstellar conditions might affect cosmic rays reaching Earth, the shape of the heliosphere, and even potentially long-term climate patterns. We are not sitting still. We are sailing slowly and silently through a galactic fog. Some moons are geologically active. Geological activity, that process of internal energy reshaping a world's surface, is not limited to planets. Several moons in the solar system show clear signs of internal energy and ongoing surface change. Io, Jupiter's innermost large moon, is riddled with active volcanoes, fueled by relentless tidal heating. Enceladus, orbiting Saturn, vents dramatic plumes of water vapor into space. Europa and Ganymede likely have subsurface oceans stirred by internal warmth. Even distant Triton, Neptune's captured moon, shows signs of cryovolcanism, icy eruptions driven by shifting pressures below its frozen surface. These moons are not static ice balls or dead rocks. They are restless worlds with their own geology, chemistry, and perhaps even the potential for biology, hidden beneath their frozen exteriors. Pluto's atmosphere comes and goes. Though Pluto is small, cold, and distant, it actually has a thin atmosphere, composed mostly of nitrogen with traces of methane and carbon monoxide. But this atmosphere isn't permanent. When Pluto approaches the Sun in its highly elliptical orbit, surface ices warm up and sublimate directly into gas, forming a hazy envelope that expands into space. But as Pluto moves farther out on its 248-year orbit, the atmosphere cools and collapses, freezing back onto the surface like frost settling on a winter morning. During the New Horizons flyby in 2015, Pluto's atmosphere was visible as a beautiful layered blue haze, backlit by the Sun, a fleeting breath of warmth around a world that spends most of its time in deep cosmic winter. Temperatures at the Sun's core exceed 15 million degrees. Deep inside the Sun, at its very center, temperatures soar to over 15 million degrees Celsius. Here, in this unimaginably hot furnace, hydrogen atoms are compressed under immense pressure until they fuse together into helium, releasing enormous amounts of energy in the process. This fusion reaction is what powers the Sun's light and heat, and ultimately, all life on Earth. The energy generated in the core takes hundreds of thousands of years to work its way outward, bouncing through layers of dense plasma like a pinball. Once it finally escapes from the surface, it travels across space in just over 8 minutes to reach us. The Sun's radiant calm, that gentle warmth we feel, hides an unimaginably hot and violent heart. Uranus has a faint, tilted ring system. Though Saturn's rings are the most iconic and famous, Uranus also has rings. 13 known ones, in fact, though they are much darker, narrower, and fainter than Saturn's spectacular bands. Made of tiny particles of rock and ice, these rings orbit in alignment with Uranus's unusual extreme tilt. Since the planet essentially lies on its side, the rings appear vertical when viewed from certain angles, rather than horizontal like Saturn's. Some of the rings are incredibly narrow and sharp-edged, possibly shaped by small shepherd moons that keep them confined. They weren't even discovered until 1977, when astronomers noticed them blocking the light of a background star during an occultation. They are subtle, shadowy bands circling a sideways planet. The heliosphere is a magnetic bubble blown by the Sun. The solar wind, that constant stream of charged particles released by the Sun, flows outward in all directions, forming a vast magnetic bubble around the entire solar system. This structure is called the heliosphere. It acts like a protective shield against galactic cosmic radiation from beyond. Shaped by solar activity and the pressure of interstellar space pushing back, it stretches far beyond Pluto, enclosing all the planets, all the comets, all the distant icy objects. Its outer edge, the heliopause, is where solar influence finally fades and interstellar space begins. As the Sun orbits the Milky Way on its own 200 million-year journey, the heliosphere moves with it, protecting the solar system as it drifts through changing regions of interstellar space, a bubble of home in the cosmic sea. Mercury's orbit helped prove Einstein's theory of gravity. For centuries, astronomers noticed something strange about Mercury's orbit. Its closest approach to the Sun, called perihelion, slowly shifted over time, rotating around the Sun bit by bit. It was more than Newtonian physics could account for, and it puzzled scientists. In 1915, Albert Einstein's revolutionary theory of general relativity provided the solution. According to relativity, massive objects like the Sun don't just pull on things with gravity. They actually warp the fabric of spacetime itself, subtly altering planetary paths. The small but measurable effect on Mercury's orbit matched Einstein's predictions exactly. This became one of the first experimental confirmations of his revolutionary theory, a quiet triumph of mathematics, explaining a peculiar quirk in the motion of a scorched, rocky world. The Moon shapes Earth's tides. The daily rise and fall of ocean tides on Earth, that rhythmic breathing of the seas, is largely caused by the gravitational pull of the Moon. As the Moon's gravity tugs on Earth's oceans, it creates bulges on the side facing the Moon and also on the opposite side. As Earth rotates beneath these bulges, they move across the globe, producing the high and low tides we see at coastlines. The Sun also influences tides, creating what we call spring tides and neap tides depending on its alignment with the Moon. Tidal forces don't just affect oceans. They can also subtly shift Earth's crust and even influence the rotation of the planet itself, very slowly over time. The Moon's silent pull keeps the oceans in constant motion, a cosmic dance between world and satellite. There may be undiscovered planets beyond Neptune. Astronomers have noticed something curious. Some distant objects in the Kuiper belt follow clustered, highly elongated orbits that can't be easily explained by the gravity of the known planets. One leading theory is that a large, as yet undetected planet, sometimes called Planet 9 or Planet X, may be influencing these distant paths with its gravity. If it exists, this hidden planet would be several times the mass of Earth and would orbit far beyond Pluto, taking thousands of years to complete a single revolution around the Sun. No direct evidence has yet confirmed its existence, but telescopes around the world are searching. If found, it would completely reshape our understanding of the solar system's outer architecture and add a ninth planet back to the family, though a very different one than Pluto. Callisto may have an ocean beneath its icy surface. Jupiter's moon Callisto appears quiet and heavily cratered, with an ancient surface untouched by recent geological activity. It looks dead and dormant. But deep beneath that frozen, battered crust, scientists suspect something remarkable. A subsurface ocean may exist. Kept liquid by internal heating, and perhaps residual heat from its formation billions of years ago, this hidden sea may contain salty water. Magnetic readings from the Galileo spacecraft hinted at a conductive layer beneath the surface, consistent with liquid water. If confirmed, Callisto would join Europa, Ganymede, and Enceladus as another ocean world orbiting in our solar system. Though less well known than its more famous siblings, Callisto's deep, dark sea could contain all the ingredients for life, silently sealed beneath a shell of ice and time. Venus is hotter than Mercury despite being farther from the Sun. Although Mercury is the closest planet to the Sun, closer than any other world, Venus actually holds the record for the hottest surface temperatures in the entire solar system. This seems counterintuitive at first, but the reason is fascinating. Venus has an incredibly thick atmosphere, composed mostly of carbon dioxide, which traps heat in a runaway greenhouse effect. Surface temperatures on Venus exceed 460 degrees Celsius, hot enough to melt lead into puddles. The dense clouds reflect much of the incoming sunlight, but they also prevent any heat from escaping back into space. Meanwhile, Mercury, with its thin exosphere and no real atmosphere, has no such insulation and cools rapidly on its night side. Venus's searing heat isn't just about proximity to the Sun. It's about atmosphere and the relentless power of trapped radiation. The rings of Saturn are made mostly of ice. Though they shimmer and shine like solid bands of light when viewed from Earth, Saturn's rings are actually composed of countless individual particles, mostly water ice, ranging in size from tiny grains of dust to chunks the size of houses or even small buildings. These icy fragments orbit in an incredibly thin, flat disk, kept in their precise place by Saturn's gravity and the subtle influence of nearby shepherd moons. The ice gives the rings their brilliant reflectivity, making them one of the brightest, most dazzling features in the solar system when seen from afar. Embedded within the rings are narrow gaps, intricate wave patterns, and delicate ringlets, all shaped by gravitational resonances with Saturn's many moons. The rings are dynamic, ever-changing structures, sculpted ice caught in endless motion. Ceres is both an asteroid and a dwarf planet. Located in the asteroid belt between Mars and Jupiter, Ceres holds a unique distinction. It's the largest object in that region, so large in fact that it qualifies as a dwarf planet, not just an asteroid. Discovered way back in 1801, making it one of the oldest known objects in the solar system after the classical planets, Ceres is spherical, unlike most smaller asteroids. It may even contain a subsurface layer of briny water or slushy mud beneath its surface. NASA's Dawn spacecraft revealed mysterious bright spots on Ceres' surface, which turned out to be deposits of salt, possibly left behind by evaporating water from below. Ceres is a hybrid world, neither quite planet nor typical asteroid, offering us a precious glimpse into the early ingredients of planetary formation. Mars appears red because of rust. The surface of Mars is coated in a fine layer of dust made of iron oxide. That's the same compound that gives rust its distinctive reddish-orange color. Over billions of years, this iron-rich material has oxidized in the thin Martian atmosphere, slowly reacting with trace amounts of oxygen. This rusty dust is so pervasive it colors everything. It coats the entire planet, gets kicked up into the atmosphere during storms, and even turns the Martian sky a peachy, salmon color during the day. Despite the rusty appearance dominating our view, Mars also has darker basaltic plains from ancient lava flows and bright polar ice caps that gleam white. But from a distance, that distinctive reddish tone dominates everything, a dusty signal of oxidation on a cold desert world. Sunspots are cooler regions on the Sun's surface. Though the Sun's surface blazes at thousands of degrees, certain areas appear darker when we observe them. Not because they're cold, but because they're cooler than their intensely hot surroundings. These are sunspots, temporary regions where intense magnetic activity suppresses the outward flow of heat from the Sun's interior. Sunspots can be larger than the entire Earth and often appear in pairs or clusters, following the Sun's 11-year magnetic cycle. They grow more numerous and active as the Sun approaches solar maximum. Despite their name suggesting darkness, they are still extremely hot, around 4,000 degrees Celsius. But the contrast with the surrounding 6,000-degree surface makes them appear dark. These spots are magnetic scars, revealing the Sun's ever-changing internal rhythms. Uranus was discovered by telescope. Unlike Mercury, Venus, Mars, Jupiter, and Saturn, which have been known since ancient times because they're visible to the naked eye, Uranus wasn't officially identified as a planet until relatively recently. In 1781, astronomer William Herschel observed it through a telescope. At first, he thought it might be a comet or perhaps just another distant star, but further observations over weeks and months confirmed its planetary motion, its orbit around the Sun. Uranus became the first planet discovered in modern times, dramatically expanding the known boundaries of the solar system. Its discovery marked a fundamental shift from naked eye astronomy, practiced for thousands of years, to instrument-based exploration. Since then, Uranus has revealed many surprises, from its extreme axial tilt to its faint ring system and its many icy moons. It's a planet that quietly rewrote the map of the night sky. The solar system is about 4.6 billion years old. By carefully studying ancient meteorites, measuring radioactive isotopes, and examining the oldest rocks on Earth and the Moon, scientists have traced the age of the solar system to around 4.6 billion years. It all began as a swirling cloud of gas and dust, called a solar nebula, which collapsed under its own gravity. The Sun formed at the center, igniting fusion in its core, while the remaining material gradually coalesced into planets, moons, asteroids, and comets. This process of accretion, collision, and differentiation laid the foundation for everything that followed, everything we see today. The planets we observe are survivors of an incredibly chaotic beginning, shaped by countless collisions, migrations through space, and long, slow cooling over billions of years. Vesta has layered structure like a planet. Vesta, the second largest object in the asteroid belt, is not just another rock tumbling through space. It's actually a protoplanet, a world that almost became a full planet. With a differentiated, layered structure. Beneath its cratered surface lies a rocky mantle and a dense metallic iron core, similar to the internal structure of Earth and the other terrestrial planets. This means Vesta once had enough internal heat to melt and separate into distinct layers based on density, a process called planetary differentiation. The giant impact that carved out the massive Sylvia crater at its south pole, visible even from Earth-based telescopes, may have actually exposed some of these deeper layers. Vesta is a frozen fossil, a planetary building block that never quite made it to full planet status, offering us a window into planetary formation. The Moon has quakes. Though it appears still, silent, and unchanging, the Moon occasionally trembles with what we call moonquakes. These can be caused by several things: tidal forces from Earth's gravity, thermal expansion as the lunar surface heats up during the day and cools at night, or even meteorite impacts. Some quakes originate deep within the Moon, hundreds of kilometers down, and surprisingly, they can last for up to an hour, far longer than earthquakes on Earth. This is because the Moon's interior is colder and more brittle. Data from seismometers left behind by the Apollo missions first revealed these subtle shakes, and new instruments continue to study them. Though the Moon has no tectonic plates and no active volcanoes, its quakes suggest an interior that is not entirely dormant, a solid world with a quiet, faint, pulsing heart. Triton is a captured moon. Neptune's largest moon, Triton, has a fascinating and violent history written in its orbit. It's unique among major moons because it travels in the opposite direction of its planet's rotation, in what's called a retrograde orbit. This unusual, backward path strongly suggests that Triton did not form peacefully alongside Neptune billions of years ago. Instead, it was almost certainly captured from the Kuiper belt, perhaps violently pulled into orbit during some ancient gravitational encounter. The gravitational disruption from this dramatic capture may have destroyed Neptune's original system of moons and heated Triton's own interior through intense tidal flexing. Today, Triton has nitrogen geysers that spew material into space, a thin atmosphere, and a frozen surface marked by strange cantaloupe-like textures. It is both a relic of the outer solar system and a moon forever shaped by a violent cosmic adoption. Neptune has 14 known moons. Neptune, that distant ice giant orbiting at the solar system's edge, is accompanied by at least 14 known moons. They range from large and geologically interesting to small, dark, and irregular. The largest, Triton, which we just talked about, makes up most of the total mass. But others like Proteus, Naiad, Larissa, and tiny Hippocamp follow eccentric and varied paths around the planet. Some are likely captured Kuiper belt objects, swept up by Neptune's gravity. Others may have formed from collisions or accumulated from debris. Most of these moons are icy, dark, and reflect very little sunlight, making them difficult to spot. Their varied orbits and compositions offer important clues about Neptune's violent past and possible migrations through the solar system. Together, they form a scattered, diverse family of companions around a planet that drifts in the cold darkness. The Parker Solar Probe is touching the Sun. Launched in 2018, NASA's Parker Solar Probe is doing something that sounds impossible. It's the first spacecraft designed to fly directly into the Sun's outer atmosphere, the corona. It moves at extraordinary speeds, faster than any human-made object ever built, over 400,000 miles per hour, and it endures temperatures exceeding 1,300 degrees Celsius. Protected by a cutting-edge carbon composite heat shield, the probe dips closer to the Sun with each orbit, gathering unprecedented data on solar wind, magnetic fields, and energetic particles. Its mission is to solve long-standing mysteries, like why the corona is so much hotter than the Sun's surface, and how solar flares accelerate particles to such high speeds. In a very real sense, it's not just studying the Sun from afar. It's flying through it, tasting the star that gives us life. Some meteorites on Earth came from Mars. Though Mars is millions of kilometers away, pieces of it have actually landed here on Earth. These are Martian meteorites, fragments of rock that were blasted off the red planet's surface by powerful asteroid or comet impacts. These chunks of Mars then traveled through space for thousands or even millions of years, before eventually falling through our atmosphere and landing on Earth. Scientists identify them by carefully comparing their chemical makeup and mineral composition to data collected by Mars rovers and orbiters. Some of these meteorites contain tiny bubbles of trapped Martian atmosphere and minerals that were shaped by liquid water long ago. They offer direct, physical clues to Mars's geological and chemical history. These wayward stones are precious samples from another world, sent to us by nature long before any spacecraft managed to return samples. The Sun is mostly hydrogen and helium. About 70% of the Sun's total mass is hydrogen, the lightest and simplest element. Most of the rest, about 28%, is helium. These two lightest elements completely dominate its makeup and fuel the nuclear fusion reactions happening in its core. Under extreme pressure and heat, hydrogen atoms are forced together, fusing into helium and releasing vast amounts of energy in the process. The remaining 1 to 2% of the Sun's mass includes heavier elements like oxygen, carbon, nitrogen, and iron, all of which originated in earlier generations of stars that lived and died before our Sun was born. Despite its brilliance, its complexity, and its life-giving power, the Sun is fundamentally quite simple in composition. A glowing sphere of primordial gases, shaped by gravity and powered by nuclear fire. Earth's tilt gives us seasons. Earth's axis is tilted about 23.5 degrees relative to its orbital plane around the Sun. This seemingly small tilt is actually the reason we experience seasons at all. When the northern hemisphere is tilted toward the Sun, it receives more direct sunlight and enjoys longer days, resulting in summer. Meanwhile, the southern hemisphere experiences winter. 6 months later, the situation reverses. Without this axial tilt, seasons would barely exist, and most of Earth's climates would be far more uniform and unchanging year-round. The tilt has shifted very slightly over tens of thousands of years due to gravitational influences from the Moon and other planets, but it remains remarkably stable. It's one of those quiet background factors, one of the invisible architects of life's seasonal rhythms, the changing leaves. The migrating birds, the cycles of growth and rest. Jupiter's magnetosphere is the largest structure in the solar system. Jupiter's immense magnetic field extends millions of kilometers into space, forming a magnetosphere so incredibly vast that, if it were visible to the naked eye, it would appear larger than the full moon in Earth's night sky. This powerful field is generated by electric currents flowing through Jupiter's interior, through a layer of metallic hydrogen created by extreme pressure. Within the magnetosphere, charged particles zip along magnetic field lines at tremendous speeds, creating intense radiation belts, massive auroras at the poles, and fierce electrical storms. The magnetic field captures volcanic particles spewed from Io's eruptions and shapes the orbits and environments of nearby moons. For spacecraft, Jupiter's magnetosphere is a major radiation hazard requiring careful planning. For scientists, it's an enormous natural laboratory for studying planetary magnetism at its most extreme. Planetary rings may be temporary. Though they appear timeless and eternal when we gaze at them through telescopes, planetary rings, including Saturn's magnificent bands, may actually be relatively short-lived on cosmic timescales. Rings form from various sources: shattered moons torn apart by tidal forces, leftover debris from the planet's formation, or icy particles pulled into orbit. But over millions of years, these materials can spiral inward due to gravity, atmospheric drag, or magnetic forces, eventually falling onto the host planet and disappearing. Current observations and computer models suggest that Saturn's rings may be less than 100 million years old, surprisingly young compared to the planet itself, and could vanish entirely within another 100 million years or so. The spectacular rings we see today may be a fleeting phase, a brief shimmering moment in a planet's much longer life. We're fortunate to live in an era when they exist in such glory. The moon's surface barely changes over time. Without wind to erode it, without rain to wash it away, without plate tectonics to reshape it, the moon's surface remains almost entirely unchanged for millions, even billions of years. Footprints left by Apollo astronauts over 50 years ago are still there, perfectly preserved in the lunar dust. They'll likely remain for thousands of generations to come, undisturbed markers of humanity's first steps on another world. The main forces that slowly alter the lunar landscape are micrometeorite impacts, constantly peppering the surface with tiny particles, and cosmic radiation gradually breaking down surface materials. This gradual process is called space weathering. Craters from ancient impacts, some billions of years old, still dominate the terrain, creating a faithful record of collisions going back to the solar system's earliest, most violent days. The moon is not only Earth's closest neighbor, it's also one of our oldest and most faithful geological archives, a time capsule preserving ancient history. Some icy moons may have hydrothermal vents. Beneath the icy crusts of moons like Europa and Enceladus, scientists believe their subsurface oceans may actually touch hot, rocky cores far below. If this is true, it could create hydrothermal vents, similar to those found on Earth's ocean floor in the deepest trenches. On our planet, such vents support entire ecosystems that thrive without any sunlight at all, using chemical energy from minerals and superheated water rising from below. These communities include strange tube worms, blind shrimp, and unique bacteria. If similar vents exist on these distant icy moons, they could provide all the conditions thought necessary for life to emerge and survive. Liquid water, a steady energy source, and the right chemistry. Plumes from Enceladus even contain organic compounds associated with biological processes. These hidden underwater worlds, sealed beneath kilometers of ice, may be the most promising places in our entire solar system to search for life beyond Earth. Secret oceans warmed from below, potentially teeming with alien biology. Sunlight takes over 8 minutes to reach Earth. The light that warms your skin when you step outside, the light that brightens the sky and makes shadows, began its journey in the sun's core through nuclear fusion, creating countless photons of light energy. These photons then take hundreds of thousands of years to travel from the sun's center to its surface, constantly bouncing and scattering through impossibly dense plasma, absorbed and re-emitted millions of times. Once they finally escape from the sun's surface, however, they travel the remaining distance to Earth, about 150 million kilometers, in just over 8 minutes at the speed of light. So when you watch a sunrise or feel the warmth of midday sun on your face, you're experiencing light not as the sun is right now, but as it was 8 minutes and 20 seconds ago. A glimpse into the very recent past, a message of light crossing the void. Europa's cracked ice may shift like tectonic plates. The surface of Jupiter's moon Europa is covered in a thick shell of ice, and it's crisscrossed with dark lines, ridges, and regions of chaotic, jumbled terrain. These fascinating features suggest the ice may actually be moving, breaking apart, sliding past itself, and even subducting, diving beneath other sections, much like Earth's tectonic plates. If this theory is correct, Europa would be the only known body in the entire solar system, besides Earth, with active, plate-like motion. The process could help cycle nutrients and chemicals between the frozen surface and the liquid ocean far below, potentially increasing the moon's habitability. The driving force behind this motion is likely tidal flexing from Jupiter's immense gravity, which continually kneads and heats Europa's interior like dough being worked. It's a frozen world, yes, but definitely not a static, dead one. It's alive with motion and change. Saturn is less dense than water. Here's a remarkable fact that sounds impossible but is completely true. If you could somehow place Saturn in a giant cosmic bathtub filled with water, it would actually float. Not because it's hollow or made of something unusual, but simply because its average density is less than that of liquid water. Saturn is composed mostly of hydrogen and helium, the lightest elements, giving it an overall lightness despite its absolutely massive size. Its volume is enormous, more than 700 times that of Earth, but its mass is only about 95 times greater, making it surprisingly diffuse and puffy. This remarkably low density gives Saturn a gentle, spread-out structure. Its rapid rotation, just over 10.5 hours per day, flattens it noticeably at the poles and bulges it at the equator. It's a giant ball of gas, softly puffed into shape by gravity, spin, and time. Solar flares can disrupt technology on Earth. Solar flares are sudden, powerful eruptions of energy from the sun's surface, often linked to sunspot activity and tangled magnetic fields, suddenly releasing their pent-up energy. These outbursts release intense bursts of radiation across the entire electromagnetic spectrum, including dangerous X-rays and ultraviolet light. When these flares are directed toward Earth, they can significantly disturb our upper atmosphere, affecting GPS systems, disrupting radio communications, and interfering with satellite operations. Astronauts in space face increased radiation exposure. In extreme cases, particularly powerful flares can trigger geomagnetic storms that potentially damage power grids and transformers on the ground, causing widespread blackouts. While Earth's magnetic field offers substantial protection, solar flares remind us that the sun is not a steady, unchanging light bulb in the sky. It's a dynamic, occasionally volatile star, one that sometimes sends ripples of electromagnetic energy pulsing across the solar system, affecting everything in its path. The solar cycle influences auroras. Auroras, those shimmering curtains of green, red, violet, and sometimes blue light that dance near Earth's poles, are caused by charged solar particles interacting with our planet's magnetic field and upper atmosphere. These spectacular displays become significantly more frequent and intense during periods of high solar activity, which follow an approximately 11-year cycle, during solar maximum, when the sun is most active. Increased sunspot activity and more frequent solar flares send more energetic particles hurtling toward Earth. These particles get funneled by our magnetic field toward the polar regions, where they collide with oxygen and nitrogen molecules, making them glow like a cosmic neon sign. During solar minimum, when the sun quiets down, the auroral lights are less frequent and less dramatic. The sun's magnetic fluctuations ripple outward across the solar system, and here on Earth, we see them painted across our skis in subtle solar brushstrokes, a reminder that we're intimately connected to our star. Comet tails always point away from the sun. As a comet approaches the sun from the cold outer reaches of the solar system, its icy surface begins to heat up and sublimate, releasing gas and dust that form that characteristic glowing tail we associate with comets. But here's something that might surprise you. The tail doesn't trail behind the comet like smoke behind a train or a cape behind a superhero. It points away from the sun, no matter which direction the comet is actually moving. This happens because solar wind, that constant stream of charged particles, and radiation pressure from sunlight itself push the released material outward, away from the sun. The result is actually two distinct tails, a curved yellowish dust tail and a straight bluish iron tail. The result is a luminous, windswept signature, tracing the invisible force of sunlight and solar wind through the darkness of space. A cosmic wind sock showing the sun's breath. Some planetary moons formed from giant impacts. Earth's moon is believed to have formed from a truly colossal impact between the early Earth and a Mars-sized body, sometimes called Theia, over 4 billion years ago. The collision was so violent it ejected massive amounts of material into orbit, which gradually coalesced over time into our moon. Similar impact origins are suspected for other moons in the solar system, such as Pluto's large moon Charon, which may have formed from a similar giant collision. These violent, catastrophic beginnings contrast sharply with the captured moons of the outer planets, which were simply grabbed by gravity. This shows that there's no single universal process that explains all satellites and moons. Some were born of fire, violence, and collision, their origins written in chaos. Others formed through gentle gravitational capture or condensed from the same disk of material as their parent planet. The diversity of moon origins mirrors the chaos and creativity of the solar system's formative years. Voyager 1 carries a golden record into deep space. Launched back in 1977, Voyager 1 now travels through interstellar space, farther from Earth than any other human-made object. Currently over 24 billion kilometers away and still going. Attached to its side is something extraordinary. A golden phonograph record, a time capsule containing sounds and images carefully chosen to represent life and culture on Earth. It includes greetings spoken in dozens of languages, music from cultures around the world, and recordings of natural sounds. Ocean waves, bird songs, wind, thunder, and even human laughter. Designed by a team led by astronomer Carl Sagan, the record is meant for any intelligent beings who might someday encounter this lonely spacecraft drifting through the galaxy. It's a message in a bottle cast into an ocean of stars. A quiet, hopeful greeting from our pale blue dot, saying we were here, we existed, and this is what we sounded like. Even if it's never found, it represents humanity's hope and curiosity reaching into the unknown. Earth shares its orbit with co-orbital asteroids. Although Earth orbits the Sun essentially alone in its path, without any planet-sized companions, it actually shares its general region of space with small rocky bodies known as co-orbital asteroids. These objects don't orbit Earth itself like the Moon does. Instead, they follow stable, looping paths near Earth's orbit, their motion shaped by the complex gravitational interactions between Earth, the Sun, and their own momentum. Some, called Trojans, hover around stable Lagrange points, those special gravitational balance points ahead of or behind Earth in its orbit. Others follow strange horseshoe-shaped paths that keep them near Earth but never quite colliding, dancing in gravitational resonance. These quiet companions are often temporary, captured and released over thousands or tens of thousands of years as orbits shift. Invisible to the naked eye, far too small to see without telescopes, they drift near us in space, fellow travelers on our yearly journey around the Sun. Neptune was once confused with Uranus. Before Neptune was officially discovered and recognized as a planet in 1846, some early astronomers may have actually observed it through their telescopes without realizing what they were looking at. Because Neptune moves so incredibly slowly across the sky and appears so dim, even through a telescope, it was occasionally mistaken for a fixed star, just another point of light, or sometimes thought to be yet another sighting of Uranus. In fact, the famous astronomer Galileo may have unknowingly observed Neptune through his primitive telescope way back in 1612, more than 2 centuries before its official discovery. He marked it in his notes as a star. It wasn't until mathematicians noticed persistent irregularities in Uranus's orbit that couldn't be explained that Neptune's existence was predicted through pure mathematics and finally confirmed through direct observation. In a sky filled with thousands of wandering points of light, Neptune remained successfully hidden in plain sight for centuries. The edge of the solar system isn't defined by gravity. The Sun's gravitational pull extends incredibly far beyond Pluto, holding on to distant comets and icy bodies all the way out in the Oort cloud, potentially a light year away or more. But when scientists speak of the edge of the solar system, they usually refer to a different boundary. The edge of the heliosphere, that region where the solar wind finally meets and collides with the interstellar medium, the thin gas between stars. This edge, called the heliopause, marks the point where the influence of the Sun's magnetic field and the outward pressure of its particle flow finally ends. The Sun's gravity continues far, far beyond this point, but the energetic, dynamic boundary is where the space between stars truly begins. It's a subtle, shifting frontier, more like a change in pressure and particle density than a solid wall, more a gradual transition than a sharp edge, the boundary between home and the vast unknown. Planetary atmospheres slowly leak into space. Even thick, substantial atmospheres like Earth's are not truly permanent over cosmic time scales, over millions and billions of years. Light gases like hydrogen and helium can gradually escape a planet's gravitational grip and drift off into space, lost forever. This process, known as atmospheric escape, is much more pronounced on smaller planets with weaker gravity, such as Mars and Mercury. They simply can't hold on to lighter molecules as effectively. On Venus, the lack of a protective magnetic shield has allowed the relentless solar wind to erode and strip away parts of its upper atmosphere over billions of years. Even Earth loses thousands of tons of hydrogen every single year, though it's easily replenished by volcanic activity and other processes. The slow escape of gases is like a quiet leak into the void, an eternal exchange between planets and the vacuum beyond. Atmospheres are not permanent gifts, but temporary blankets that must be constantly maintained. Some moons may have formed from ring systems. Just as ring systems can gradually decay and fall into planets or vanish over time, they can also, under the right conditions, give birth to new moons. It works in both directions. In Saturn's case, it's quite possible that some of its small outer moons originally coalesced from ring material that slowly clumped together beyond what's called the Roche limit. That's the boundary beyond which gravity can successfully pull matter together into moons rather than tearing it apart into rings. Small moons like Pan and Daphnis, which orbit within or very near Saturn's rings even today, may still be slowly accreting material from the rings around them. These tiny moonlets serve as quiet sculptors of the ring system, their modest gravity carving distinct gaps and creating waves in the icy bands around them. It's a beautiful example of how dynamic and interconnected these systems are. Rings becoming moons, moons shaping rings, all in a slow cosmic dance. Voyager 1 is still sending data from interstellar space. More than 45 years after its launch, an almost incomprehensible achievement in engineering, Voyager 1 continues to transmit faint signals back to Earth, even as it travels through the interstellar medium, billions upon billions of kilometers from home. Its aging instruments still measure cosmic rays, magnetic fields, and plasma density in the space between stars, regions no human-made object has ever explored before. Power is increasingly limited as its nuclear generator slowly decays, and systems are being gradually turned off one by one to conserve energy. But the spacecraft still functions, still communicates. It uses a tiny plutonium-powered nuclear battery and sends its whispers home via NASA's Deep Space Network. Every signal now takes more than 22 hours to reach Earth, traveling at the speed of light. A faint whisper from the very edge of human exploration, still telling us stories about places we've never been. The solar system completes a galactic orbit every 225 million years. While the planets orbit the Sun in their annual dances, the Sun itself is also moving through space, not sitting still. It revolves around the center of the Milky Way galaxy in an enormous orbit. It takes roughly 225 to 250 million years to complete one full orbit around the galactic center. This immense journey is sometimes poetically called a cosmic year or a galactic year. During that incomprehensibly long time, the solar system drifts through different regions of interstellar space, potentially passing through spiral arms of the galaxy, star-forming regions filled with gas and dust, and vast empty voids between structures. This motion through different galactic environments may influence long-term comet activity, and on even longer timescales, might even affect Earth's climate and the frequency of mass extinctions. We are not fixed in space, but part of a vast, slow spiral, riding one of the galaxy's arms like passengers on a cosmic carousel that takes hundreds of millions of years to complete one revolution. The last dinosaurs that walked the Earth lived during a completely different galactic position than we do now. That's how long these cosmic years truly are. And so, our quiet journey through the solar system comes to a gentle close. From the inner world scorched by relentless sunlight to the icy moons that whisper secrets in the dark, from supersonic winds howling on Neptune to hidden oceans beneath Europa's frozen shell, from ancient volcanoes towering on Mars to worlds where diamonds might rain through alien skies, we've wandered together through orbits, storms, and shadows, one sleepy fact at a time, letting each one wash over us like a gentle wave. We've learned about planets that spin backwards, moons that orbit the wrong way, rings that are slowly disappearing, and ice hiding in shadows on the hottest worlds. We've discovered that the sun sings songs we cannot hear, that some asteroids have their own tiny moons, and that two little spacecraft launched decades ago are still whispering to us from beyond the edge of the solar system. We've explored worlds with methane lakes and nitrogen geysers, planets wrapped in deadly radiation, and ancient craters preserving footprints that will last for millennia. We've seen how Mars turns red with rust, how Saturn could float in water, and how Venus became a furnace despite once perhaps being more like Earth. If your eyes are already heavy now, if sleep is starting to pull at you, that's perfectly fine. That's exactly as it should be. Let the last traces of starlight fade gently behind your thoughts, like the sun setting on a distant world. Let your breath carry you softly, easily into rest, like a spacecraft drifting on solar wind. There's still so much more out there to discover, so many more wonders waiting in the darkness beyond. Mysteries we haven't solved yet, moons we haven't visited, questions we haven't even thought to ask. But for now, for tonight, you've learned enough. You've traveled far, farther than most people travel in their dreams, across billions of kilometers of space without ever leaving your bed. The planets will still be there tomorrow, spinning patiently in their ancient paths, exactly as they have for billions of years. The moons will still orbit their giants. The sun will still shine, still sing its silent songs. The rings of Saturn will continue their slow reign toward the planet below. And when you wake, refreshed and rested, they'll all be waiting there to share more of their secrets with you. The universe is patient. It has waited billions of years already. It can certainly wait until morning. Thank you so much for spending this quiet time with me, for drifting through space together, for letting these stories of distant worlds and cosmic wonders ease you gently towards sleep. I hope they brought you some peace tonight, some sense of wonder, some feeling of how vast and beautiful and strange our little corner of the cosmos truly is. I hope these facts and stories helped you remember that we're all part of something much larger than ourselves. We are residents of a small blue world orbiting an ordinary star, in a solar system full of extraordinary neighbors, in a galaxy containing hundreds of billions of other stars, in a universe that stretches farther than we can possibly imagine. And yet, here we are, conscious beings able to look up at the night sky, to wonder about those distant lights, to build machines that can visit those worlds and send back pictures, to piece together the stories written in starlight and planetary motion. It's something worth marveling at, even as we drift towards sleep, especially as we drift towards sleep. And so, under the quiet stars, beneath the patient gaze of distant worlds spinning in the darkness, beneath rings of ice and moons of mystery, the story continues. Always continuing, always unfolding, always waiting for curious minds to discover new wonders and ask new questions. The cosmos is vast, but it's also home. And tonight, you've traveled through a little bit of it, one peaceful fact at a time. I hope you sleep well tonight, deeply and peacefully. I hope you dream softly, gently of beautiful things. Perhaps of diamond rains falling through blue clouds on distant ice giants, or of frozen oceans hidden beneath ancient ice on alien moons, or of tiny spacecraft carrying golden records full of Earth's sounds into the endless dark between the stars. Perhaps you'll dream of standing on Mars, watching the sun set in a peachy sky, or of floating above Saturn's rings, watching them shimmer like scattered jewels, or of seeing Earth rise over the moon's horizon, a fragile blue marble hanging in the blackness. Or perhaps you'll simply sleep, quiet and still, as the Earth carries you through space at thousands of kilometers per hour, as we all orbit the sun together, as the sun itself carries us on its long journey around the galaxy. Either way, you'll be traveling through the cosmos, even in your dreams. Sweet dreams, fellow traveler. Rest well. The universe will still be here in the morning, full of wonders, waiting patiently to share more of its secrets with you. Good night. Sleep well. And thank you for exploring the solar system with me tonight. Until we drift through the stars again, safe travels through your dreams.